Hello! So in the last video you saw the starts of a crazy game I was making using a little inspiration from whack-a-mole and floppy disks. In this video we're going to complete the build, write the code and finally play it. So first up, we need to be able to control these individual disk units. Now on each one we have a motor to control the spring strength, two limit switches so we can see where that spring actually is, an LED which is actually an addressable RGB LED, and an eject button. Finally, we have the lock mechanism to actually eject the disk. So in terms of connections, that's two for the motor so we can reverse the direction, two for the limit switches, one for the eject button, one for the data feed into the RGB LED, one for the switch that's inside the lock that we can use to see if the disk has been inserted, and finally the lock itself has the solenoid, so we need one more pin for that. That's a total of 8 pins. Now, the RGB LEDs can actually be chained together, as I've cut them out from a strip of individually addressable LEDs. So I can leave that out and that leaves us 7 pins per drive bay. And given there's 5 of these, I'm going to require over 30 I/O pins. And rather than messing around with multiplexing, I've decided to simply use more than one Arduino and link them together. The first thing I want to focus on is that variable spring strength code, and it's actually quite simple. I'm going to allow commands to be received from the serial port. Each command will consist of a single character, which will simplify the communication, no need for any synchronization. The other rule I will have is that an Arduino is only allowed to send a single byte in response to a received one, and then only if it actually understood the command. This way, I can link all the serial ports together in parallel and everything should just work properly, with the ones that don't understand some commands simply ignoring them. So, to control the motor that controls the strength, I wrote a small C++ class. It starts off with a constructor, where I can pass in the pins used for the motor and the pins used for the limit switches. I added a simple function to reset the class as well, which also acts as a stop function by setting both the motor outputs to low. The motor will only turn on if one output is different from the other. I then created two simple functions that will return true if the motor has spun all the way to the top or the bottom. Then I use these two functions in the move spring down and move spring up functions. These functions are almost identical, and the first thing they do is exit the function if the motor has already reached that position. Next, it sets a direction variable for which way it wants to move and then stores the time that the movement actually began. Finally, I created a function called run. This must be run continuously in the main loop. This checks which direction the motor should be running and watches to see if it hits the appropriate limit switch, at which time it calls the reset function. There's also code in there to see if the motor has been on longer than a specified amount of time. Originally I'd planned to use this to have multiple different strengths, but in the end this is just a safety check to make sure the motor isn't on for too long or if something goes wrong. Next, I want something to monitor the eject button. Now that sounds really simple, but I want to monitor and debounce that signal too, so I wrote another class, possibly a little over-engineered, but it works perfectly. The constructor takes a single port pin and then has a run function which handles the rest. If the button is detected as down and it hasn't been pressed yet, we make a note that it has now been pressed and store the time that actually happened. And if the button isn't pressed, i.e. it's been released, and it's been more than 200 milliseconds, then we can release that pressed state. However, the class still holds on to the fact that the button has been pressed. And this can be read using the final function, which after being called, resets this information. With these two classes, I can now define everything for the first Arduino, and have it able to control the first 3 drives. This is much cleaner than writing the code for each one individually. If there'd been more than 3, I'd have probably put them all in an array and looped over them. So the only thing left here is to actually handle the messages received and send a message back. So let's take a look at the handle command function. This looks at the command received and performs the required task. If the command is not understood, the function just exits early. Each of the commands received is a simple character, making the communication easy to test from the Arduino IDE as well. Finally, after a successful command was processed, the program sends back the status of the Arduino. Unlike the messages received, this one is binary and each bit has a special meaning. If you remember, inside each of the locks is a switch that can sense if the lock is closed or not. If a lock is closed, then bits 0 to 2 are set, corresponding to the first 3 drives. The next 3 bits are set if the eject button has been pressed for each of those drives. Finally, the upper 2 bits are actually an ID number so that when the data is received we can tell which Arduino it's actually come from and therefore understand the data supplied. So that covers the first 3 drive bays, and as you imagine the other 2 are handled in much the same way but on a second Arduino sharing a lot of the same code. However, because there's only 2 drive bays on the second one, it means we've got some spare port pins, and I'll put them to good use to eject the discs from the drive. It may seem weird to create a class for controlling a simple solenoid, but that's exactly what I've done. The reason is that when triggered, I only want it to be switched on for a short amount of time, so the class, when triggered, will hold it on for 150 milliseconds. This prevents the solenoid getting too hot, but it's also long enough to perfectly eject the disc. With this being a special class and having enough free port pins for all 5 drives, the main loop for the second Arduino actually looks like this, with the extra run functions for the 5 triggers. This makes the handle command function look like this. Note how this now controls drive 4 and 5, ignoring the commands for the first 3, along with the 5 trigger commands. Finally, the send status function has been updated, noting that it only sends the status for the 2 drives. However, this time it sets bit 6 and 7 to 1, to indicate the message is coming from Arduino number 2. So that covers the operation of the drives, but there's still a few things left that aren't controlled, and that's the job of the third Arduino. This one is responsible for communicating with the LEDs to set the colour, as well as reporting the status of 2 additional buttons I've added to the back of the unit. One will be used to toggle the difficulty of the game, and the other one will be used to start it. In future, I may also add 2 further pins to light these up as required, and there's plenty of spare pins to do that with. And this starts with including the fast LED library and defining 5 LEDs. Then I've created a function that's used to apply the colour to each LED. The colour chosen is based on the lower 3 bits in the variable value passed in, with bit 0 being blue, bit 1 being green and bit 2 being red. Bit 3 configures if the LED should be flashing or not. Reusing our button class that we used in the previous 2 Arduinos, I created a main loop like this. The first section that looks a little bit complex is just handling making the LEDs flash if that was requested. The second half is much like before. There's 5 commands, 1 for each LED. However, these commands are broken down into a number of bits, where the 7th bit is always 1, which kind of means LED mode. The next 3 bits describe which LED to apply the colour to, and the remaining 4 bits are as I described before, the colour and the flashing status. Finally, they all send a message back, just like before, except whereas Arduino 1 set bit 7 to 1 and Arduino 2 set bit 7 and 6 to 1, this one just sets bit 6 to 1, followed by bit 1 and bit 0 used to indicate the press status of the 2 extra buttons. So that's the Arduino code, but now we need to look at the physical wiring. Whilst the limit switches can be directly connected to the Arduino, the eject trigger solenoid and the motors can't. So, I'm using one of these little MOSFET modules that uses the FR120N device to trigger the solenoid to eject the disc. They're very simple to use and are much more efficient than using one of those relay modules to do the same thing. They're also opto-isolated too, keeping the Arduino safe. And yes, I could have just bought a bunch of MOSFETs and made my own, but this was quicker. Now you may have noticed in the previous video when I was doing the wiring for the solenoids in these switches that I installed a diode inside the wiring. This just prevents any back EMF from destroying this part, as well as keeping EMF spikes to a low. As for the motors, well, I found these boards based around the L291N H-bridge driver chip. Each board will actually drive 2 motors, and if you provide it with 12 volts, it will actually generate a 5 volt output for you, perfect for powering the Arduinos. As I need 3 of these, this is ample amount of power for everything I'll be running, including the LEDs. Each motor needs 2 inputs. If they're both the same, i.e. both high or both low, the motor is stopped. If one is high and the other is low, the motor spins in one direction. To reverse the motor, you simply swap those high and low states. Given the amount of time the motor driver will actually run for, and also the short amount of time the eject solenoid MOSFET will actually be on, it's unlikely that anything's actually going to get particularly warm. Now, all this needs to fit into a small vertical space in one corner of the box, and I have found a way to squeeze it all in, although it was actually quite difficult. I assembled all the parts onto a thin piece of plastic, looking like this. Yeah, I know it's not pretty, but it's very functional. The top photo, starting from the left hand side, has 5 MOSFET boards, then 2 Arduinos, and then a connector for each drive. This connector carries 5 volts, ground, and the signals from the 2 limit switches, the button, and the lock switch. It also has an LED data in and an LED data out pin. The bottom photo shows the 3 motor driver boards along with some more connectors. These connectors are dedicated to the 12 volt side of things, which includes the motor and the eject solenoid. Once assembled into the case, without the lid, it looks a little bit like this, and you can see there really isn't much room in there at all. This ribbon cable you can see here comes from the board at the front and sends 12 volts, receives 5 volts, and has a ground connection. the transmit and receive signals for the serial data, and the data signal for the LEDs. And some of these connect to the other Arduino, which hides in the space in the upper right corner. Finally, the output from this will need to connect to the Amiga. So the serial send and receive lines will need converting from TTL 5V signals to proper RS-232 signals. And this is easily achieved using this little converter module, which uses the MAX3232 converter IC to perform the level conversions. Leaving finally the interesting job of finding a suitable serial cable, as the majority of the ones listed were crossover cables, also known as null modem cables. The adapter on the right finished the job by connecting the 9-pin cable to the Amiga's 25-pin serial connector. So that's all of the hardware done, and I was able to test each of the commands individually from the Arduino IDE, so I knew they all actually worked properly. The next task is on the Amiga side, and that's to make some kind of game out of it. Now I want the game to be kind of a bit like whack-a-mole, except if a disc is out and the light flashes, you have to push it back in again, and if the disc is inserted and the light flashes, you need to press the eject button. The game will be built using AMOS, and to start with, I'll create some basic functions to control the device. So first, we start by initializing the serial port, and luckily AMOS has built-in commands for handling it. The first opening the port and the remainder configuring it. The serial buff command controls the size of the buffer used to communicate with the serial port in bytes, although I've discovered this only really applies to the incoming data. Once connected, we want to reset the device into a known state, so I've created a reset procedure which calls a bunch more procedures. So let's take a look at each one of those in turn. The first one, set LED off, does exactly what it says. It turns all of the 5 LEDs off by working through each one in a loop and calling another procedure, set LED. This procedure constructs the single byte message that we need to send to control a single LED in the same format we saw when looking at the Arduino code. This also uses a global array so we can keep track of the current LED setting, so not to waste time by sending messages if it doesn't actually need to change anything. You'll notice that this then calls another procedure called send, which is very simple. It starts off with a little while loop. This causes the program to wait until all the remaining data has been sent before sending some more. This prevents too much data getting queued up, which will eventually lead to an error. Straight after the send command, we have the handle response procedure. This is a catch-all procedure designed to read and process any responses from the Arduinos. It first attempts to read from the port, and if it finds some data, it will look at the top 2 bits, bits 7 and 6, to identify which Arduino the message came from. Using that information, it decodes the remaining bits and stores the status of the buttons and switches in some more global arrays. Because the button states reset after they've been read, they're stored here in a way so we don't lose that information. This procedure also keeps a bit mask of which Arduinos it's actually received data from. We'll use that later. Now, backtracking a minute through the procedures, we get back to the reset procedure, and the last thing it calls is reset buttons. The purpose of this is to clear any information about pressed buttons, so it calls the fetch status procedure to update this before resetting all of the status variables. The fetch status procedure simply sends the 3 status fetching messages and waits for a response. The overall success of the responses is returned by the procedure. For example, if the procedure returned a 7, then all 3 Arduinos would have reported their status. Now, there's a few other useful procedures we're going to need, including one to trigger the ejecting of a disk, which you can see is actually very simple. I also created a second one to change the LED colour to a preset one based on a number between 0 and 7. Finally, we need a procedure to control the spring strength of each drive, and as you can imagine, yet again, it's actually quite simple. Now, onto the actual game, and for the game screen I've designed this simple image, but there's a few sneaky things here. First, you can see with the score at the top I've added the digits 0 to 9, and I've also got the easy and hard graphics as well. Next, beside each drive you can see the text eject disk and insert disk. We'll need those later on as well. At the bottom you can see the end of a blank disk. Originally I was going to have an insert disk animation, but this actually worked better. These different things I will capture as a bob or an image block so I can paste it onto the screen as required. You'll also notice each drive LED is a slightly different shade. This is because each one has its own unique palette entry, meaning we can just set the RGB colour rather than redrawing it. Finally, well, it looks like each drive has a set of purple lips. I'll use AMOS's rainbow command to create gradients of the correct colour for each one of these to give some depth. After grabbing all of the bobs and preparing the display, using some code looking like this, which you can see creates rainbows and then grabs various parts of the screen, the game screen ends up looking like this when ran. Now to get that score area working at the top, and knowing this is a double buffered screen, I've written a short procedure to display the score. This assumes that Bob images 24 to 34 represent the number 0 to 9. And if I use the set LED commands I created before to change the LED colours, I'd like that to also be reflected on the screen. And that's what this procedure does, because colour palette 2 to 6 are the LEDs in those drives on the screen. Now before the game starts, I'd like some kind of 3, 2, 1 countdown. So, I've pre-rendered this block of text that I can use, and I've also rendered some text for the game over part as well. And with this procedure, first I unpack the image into a hidden screen, and then create another at exactly the right height. I then make it appear in the middle of the screen, expanding from the top and the bottom. The next big for loop slides in the get ready 3, then 2, then 1 screen at a time, before hiding it. You'll notice the PT Sam play function here being called as well. Well, it's got to make some sounds, right? Anyway, let's run this procedure and see what it actually looks like. That's not bad. As for game over, well, that's almost the same. Looking at the right hand side first, it does most of the same, except this time, once it's slid in, it monitors the state of the 2 buttons on the back and the keyboard. If any of those get pressed, then the game over message disappears. The left hand side, however, that's a bit more complex. First it sends the reset command. This winds all of the motors down to their least springy state. Then it stays in a loop until all Arduinos have reported their status, or until 1 second has passed. Finally, it plays the game over sound before entering a special loop. This attempts to eject all of the disks in the drive. Now you may be wondering why a loop for this is needed. Well, there just isn't enough power to trigger all 5 ejects in one go, unfortunately, so this works through them all until they've all ejected. So let's take a look at that in action. Perfect so far. Now, the game is going to be 30 seconds long, and I want a piece of music to cover that amount of time. Something that starts off fairly calm and becomes more and more crazy. So, I reached out to Hoffman, showed him a short video of what I've created, and he went away and created this tune for me, called Disc Menace. Isn't that absolutely perfect? It gets more and more intense and lasts exactly 30 seconds. Thanks Hoffman, and I love the floppy drive sounds as part of the track. Anyway, the last part of this video is actually making the game. So let's continue to look at the code. This block of code prepares the game. Before anyone can start playing, all the discs have to be inserted. The second half of the code looks to see which locks are set, i.e. the switch that says that there's a disc inside the drive. If there is, it sets the LED to green, and if not, it sets it to a flashing white, and it also flashes the disk image bob over the drive. Lastly, and for no reason at all, I added some code for eject, totally not required. Once all the discs are inserted, the code will continue, and we'll start the countdown we saw before. So let's see that in action. Perfect. So, after the countdown, I've defined a bunch of constants so we know what state everything's going to be in. Depending on the difficulty, I've also set some more constants for how long things last and what the penalty is for getting actions wrong. Then I reset all of the arrays and set some random delay before anything can happen for each drive. Finally, we start Hoffman's excellent ProTracker module playing. Then, the main loop starts, and the first thing we store is a copy of the current state of any of the locks, i.e. if there's a disk in the drive or not, because later on we can detect this change and see if a disk has been inserted. Then we calculate how long is left in 50Hz ticks and in seconds, along with drawing that on screen, or rather erasing the time bar. Now we really need to keep up to date with what's going on with the Arduinos, so if there's nothing currently being sent, we query the 3 Arduinos individually, and then we also mop up any status messages being sent back. Now the next bit is where the fun begins. If a sufficient amount of time has passed or all 5 drives are actually idle, and we're not sending any data to the serial port, we pick a random drive bay, and if that one isn't idle we just try again one more time. If that one's idle and we're past its delay timer, we trigger an action on it. If there's a disk in the drive, we randomly choose whether to just eject it and ask them to insert it straight away, or ask the player to eject it. If there isn't a disk in the drive, we ask them to insert it. With that out of the way, the rest of the code just monitors the state of each drive and applies the rules depending on what state they're in and if anything has changed. The first state we come to is reset spring. This is triggered after each action completes and decides if the motor should wind the spring up or down to change how much the disk pings out. If we're in the insert wait state, it means the game has ejected the disk and we're just waiting for that signal back to say that the disk has actually been ejected. And when it has, it puts it into the please insert disk mode. If the player presses the eject button, then, if there's a disk in the drive, we trigger its eject as requested. Now if the game was expecting us to do that, we get a score awarded to how quickly we did it, and if not, we deduct a penalty. If, at the start of the loop, no disk was inserted, but now there is, then, like before, if it's what's expected, points are awarded. If not, they're deducted. If the drive is expecting us to eject it, it monitors how long is left and flashes the eject disk message on screen. And the same goes for the game asking us to insert the disk as well. Finally, there's a little bit of code for delaying any further actions, just to add a little bit of stillness. And with all that combined, we have a completed game. So, let's take a look at it in action. It works quite well, doesn't it? And all it needs now is a title screen, but I'm not going to bore you with that. Now I did take this along to Zzap Live a week or two ago, and many people had a lot of fun playing it. So here's a short video of me demonstrating it, and I'm sure you'll agree, the phone camera just doesn't do a good job of reproducing the music. There was a few small bugs I fixed during the event, and the only other issue was you have to press quite hard to insert the discs, which can leave your fingers a little bit sore. However, it certainly is fun to play. Also, the speaker I was using really just didn't do justice to Hoffman's track. So next time you see this, which will be at the Retro Computer Museum in Leicester on the 21st of June for their awesome world famous legendary gathering event, I'll hopefully have a better speaker with me with more bass, so I hope to see some of you there. Now, I'm not planning on publishing the designs for this thing, it's just a little bit too crazy, but please contact me if you want to know more. I hope you found this video interesting, don't forget to like it and subscribe to my channel. Thanks for watching, and I'll see you in the next one.